Welcome back to the main auditorium, where we are delighted to begin the Quantum Technology and Innovation track. To moderate our first talk in this topic, I am thrilled to introduce you to Silvia Zorzetti. Silvia is a senior engineer at Fermilab, and she is currently deputy head for the co-design department at the US National Quantum Information Science Research Center. She joined Fermilab in 2017 as a Bardeen Fellow, and during her PhD in Electronics, Engineering and Information Technology from the University of Pisa, she was a Marie Sklodowska-Curie Fellow at CERN. Thank you, Silvia.
Thank you for the introduction. I'm delighted to be here with you all at the second collisions, and it is an honor to introduce the next speaker. In fact, it is quite rare to meet someone like Markus Pflitsch, who is an expert in both the scientific and financial sectors. Markus is a co-founder and chairman of Terra Quantum AG. He is a quantum physicist and CERN alumnus. He is also an experienced senior financial executive and deep tech entrepreneur. He's a graduate physicist. As a graduate physicist, he began his professional career at the Boston Consulting Group in Europe and North America, and went on holding several top management positions like CEO, CFO, COO in international financial corporations like Deutsche Bank, UniCredit, as well as owner management, digital and high-tech companies. Markus is the co-owner of a large German multifamily office and senior advisor to private equity funds. He is also a member of the BBUG, which is a German institution which helps cultivating the next generation of executive leaders by bringing together discussion makers from business, politics, and societies. The title of Markus' presentation today is From Physics to Finance and Quantum Tech Frontier. Markus, please, the stage is yours.
Thank you, Silvia, for the very kind introduction. And I'm very happy to be back at CERN. Actually, I'm looking back now at my active time at CERN 25 years later. So it's really great to be back again. And today I would like you to lead you a little bit through my journey since my time at CERN, then into financial services and investment banking, and then finally, founding one of the leading global quantum tech companies. So I'm very happy to be here and to share my experience. This picture actually is not 25 years old. It's actually very recent, just before COVID. I invited 60 top executives from large German corporations to visit CERN, to go underground and actually to experience CERN live and see the experiments. And I can tell you that they have been all blown away by that experience. Although they are very experienced executives, they have never been there before. And for me, it was great to see actually that, what they impressed so much is still there, and it's kind of the same what has very much impressed me back then 25 years ago. So I think that is a sign of a very strong culture CERN has, and that's also why I'm still a very proud ambassador of CERN, that great organization. To let you know what I did in terms of research back then, I was researching the field of quantum chromodynamics, actually. Some of you might have heard running alpha S, and I was actually measuring running alpha S at rare events where the electron or the positron, back then it was still lab, as you know, and I was working at the Opal experiment. So therefore the electron or the positron radiated a photon before the collision, and therefore I was analyzing events at a lower energy, and therefore could find a measurement for alpha S at low energies. So that's what I did back at my time at CERN. But actually, the key learnings or takeaways from my time there were, of course, a little bit more general and didn't have so much to do with running Alpha S. I think what was more of a kind of general impact are three things. First of all, during my time, actually, the internet era actually kicked off, and that CERN has been instrumental. We all have worn those T-shirts, www.cern.ch, where the web was born, and I personally think actually that this, if you will, spin off from CERN was a great achievement, and it showed me, how exponential innovation can actually change the world. And the approach of CERN to really tackle the big questions and to support big innovation jumps really made an everlasting impression to me. And then secondly, the whole culture and philosophy of science for peace, the open atmosphere, the international atmosphere, I think have been very important to my life because it showed me that if you have the same passion, if you share the same goals, in that respect, the same scientific goals, that really unifies the world. And last but not least, it was actually that really global and diverse culture which impacted me a lot, because back then, that was mid of the 90s of the last century, CERN already was a truly global organization, and it is of course very impressive for a young person to see kind of people from all parts of the world working together in a joint project for a joint goal, regardless of their very diverse backgrounds. So I think these were actually the impressions which actually really had an influence on my life. And I then decided, after my time at CERN, to do something completely different, because I wanted to have the complementary experience, actually. So I decided to join a strategy consultancy, Boston Consulting Group, and went from Europe to North America, and actually were able to do decisive work, let's say, in the first wave of digitalization. It was the dot-com bubble back then, and everybody wanted to work in e-commerce and in the evolving and emerging internet space. So I had the chance to do that at BCG, and therefore it was kind of great to see the continuity from my time at CERN, where actually the web was born, and then actually to work on commercialization strategies of the emerging internet. My time at BCG then led me to focus on financial services and investment banking. So therefore, consequently, I joined Deutsche Bank and worked in investment banking since then in the M&A area. And that was also a very good and steep learning curve. At the beginning of the last century, there was a lot of M&A activity, actually. So it was a tremendous times. And as with BCG, I was able to look into various industries and verticals, and therefore learn a lot in terms of the global economy. I then, and also here that was a decisive kind of turning point in my life, experienced the financial crisis in 2009, Lehman crisis, and decided to leave banking to work actually in very operational roles as a chief executive officer or a chief financial officer in companies who were backed by private equity funds, leading these funds to an exit. And here, I think I gained the experience to actually also lead the company and make decisive changes for the future development of these. And that then altogether led me to the conclusion to actually put together, combine those kind of two sides of my brain, if you wish. So my education in physics, my time at CERN working as a quantum physicist, and then also using kind of the next 20 years of my career, where I have been in financial services, in corporate finance, in kind of the commercialization space. So I thought it's a good time actually to combine those two experiences, and so I founded Terra Quantum. Terra Quantum is a Swiss-based quantum tech scale-up company. It today employs around 100 quantum physicists and mathematical physicists. So it's one of the largest global teams in that space. And we are actually developing solutions and applications for quantum computing. Let me tell you a little more about that. You all know Richard P. Feynman, one of the great physicists and Nobel Prize winner. He, in the late 80s, actually said, nature is quantum, so if you want to compute like nature, you should actually do quantum computing. And that actually kick-started the development of the quantum computing era and the first kind of hardware activities in that space. And for me, it's really fascinating that the basic principles actually of quantum physics, which we know now by almost 100 years, are the decisive basic principles which make a quantum computer work. Especially the combination of the two principles you all know through your studies, superposition and entanglement. The combination of those two actually creates the exponential speed up of a quantum computer. And that is why this technology is so disruptive. That's why I personally think quantum tech is the most disruptive technology for the next decades, actually. And it will disrupt, I think, almost all verticals, because everything which has to do with simulation and optimization and machine learning will be, enhanced and upgraded by quantum applications. And if you can rely on an exponential speed up, you will soon be able, once you have the hardware which has enough qubits, you will soon be able to calculate and optimize things where today's supercomputers would take longer than the lifetime of the universe, actually. A future quantum computer, which is powerful enough, will do that in a fraction of a second. And I think this illustrates the disruptive power quantum computing will have. And that's why it's so thrilling to work in that space. And here you see how our company is organized. We actually operate in 3 business units, but the unifying theme is that we are an end-to-end quantum as a service company, because we want to tackle real life use cases and make an impact into the corporate world already today. And I will show you that this is actually possible with today's technology already. So we develop quantum algorithms and provide them for industry use cases. And then we also bring the hardware, that's our second pillar, quantum compute as a service, where we can actually deploy those algorithms and make a difference today already with migrating quantum algorithms or traditional use cases into the quantum space. And then our third pillar is quantum safety as a service, where we develop leading quantum cryptography solutions as quantum will will make it necessary that kind of all data security is upgraded to a quantum safe level. So let me go into each of those dimensions to give you a better understanding of what we do here. This actually is an example of a quantum algorithm which is based on a hybrid quantum neural network, and that one serves for better image recognition. And as you can see here, this you can use in e.g. autonomous driving for the automotive industry. But of course, better image recognition you can also use for various other verticals like robotics or medical diagnostics. And that is actually the power of the underlying quantum algorithms, that you can use them for multiple use cases in various industries. We recently developed a quantum algorithm which is used for collateral portfolio optimization within investment banks. And we could show that based on real data, that if they migrate their classical optimization algorithm into the quantum space based on the quantum algorithm we have developed, that they will save 120 million euro annual recurring cost. So that really means that has a huge business impact if you can, save costs in the order of more than 100 million each year by just migrating one single use case into the quantum space. And that is actually achieved already today using our quantum algorithms, but also our hardware, which we provide. And I will show you how that works. And we join kind of the second business unit of Terra Quantum, Quantum Compute as a Service, where we do our hardware projects. The current era of quantum computing is called NISQ era. So we have NISQ devices, that's noisy intermediate scale quantum computing devices. And you call it like this because those qubits or the QPUs are very noisy. So you have to error correct, and therefore the real performance of the available chips, e.g. the 55 qubit from IBM, is much lower, right? And therefore also the quantum volume, which is a measure for kind of how complex operations you can actually carry out with a quantum computer, is still very low. And that's why in that era of quantum computing, we are actually using classical high performance computing architecture, which we compose in an IP relevant manner, to virtualize qubits. So we work with so-called logical qubits, and those logical qubits have no errors. So you don't need to error correct. They have no noise. They are highly performant. And that's why with our machine, the QMware platform, which is accessible via the cloud, we have a quantum volume which is much higher than all available kind of true QPUs. And that makes it possible that we achieve those business impacts, which I talked about earlier, already today. And that is decisive because to gain commercial traction and to have successful quantum use cases for the industry is very important, so that the industry really kind of enters into quantum technology and is not waiting kind of years until we have real QPUs which are higher performant. So with that compute power, actually we tackle a lot of use cases, and the corporates can access our platform via the cloud and can experiment with their own developed quantum algorithms, or they join forces with us and we co-develop such algorithms. Let me jump to the last business unit, and that is quantum safety as a service. And I would like to talk a little bit about data security. We all know since Peter Shor and his great algorithm that every classical encrypted code will be hacked by a future quantum computer which has enough qubits. So there is no real quantum safety in classical encryption. And that's why actually the industry has to upgrade to a quantum safe level. And we actually made some breakthrough contributions here. First, we were able to show that we mathematically could reverse the hash function. And that means that we could break various classes of classical encryption algorithms with a quantum computer. And that includes AES, the Advanced Encryption Standard, which was so far being reviewed as a quantum robust encryption algorithm. And this also has a lot of consequences, our work, which we also, to mention that, can't yet practically execute because we don't have the hardware yet which has enough qubits. But it has a lot of consequences because it means also that all existing blockchain protocols, for instance, are not quantum safe and therefore are vulnerable once the hardware is there to execute our protocol. And that means there is a quantum threat to organizations. And that's also why recently an expert of the industry said, prepare for the quantum hack now. You have to upgrade data security to the quantum level because you can't wait until the hardware is there because then it is too late. Therefore, we put a lot of effort in the development of a truly quantum encrypted protocol to exchange data and to communicate safely. And we were able to develop a protocol based on fast quantum key distribution, which, because we have a revolutionary approach here in sending a bunch of photons instead of just one photon, we could actually achieve a long distance, fully quantum secure data exchange. And we can also work with existing optical fiber infrastructure because we got rid of so-called quantum repeaters or trusted nodes along the line, which is a tricky thing to do because of that bunch of photons which we send. So therefore, we can work with existing fiber combined with commodity optical amplifiers. And that makes it very powerful because fiber infrastructure is there and is installed, and we don't have to wait for a future satellite infrastructure, which, by the way, our protocol also works. But a satellite infrastructure has a lot of unsolved problems, e.g. the satellites have to act as trusted nodes. You have some last mile issues here, and it's, by the way, very costly and still, 10 plus X years down the road. So what we created is actually an implementable protocol, and that's, of course, also very thrilling. And also this is a very commercializable product because, as I told you, you have to make sure that you are quantum safe before the hardware is there. And actually, if we look at the roadmaps of some of the hardware developers, we can see that this might happen pretty soon, as there are some revolutionary technologies underway which could get rid of the mechanical challenges. And therefore, I expect that we see some innovation leaps actually on the hardware side, which will make it able to much faster scale the existing numbers of qubits and make them higher performant. So that was kind of a tour d'horizon about what we do at Terra Quantum. It also was kind of an overview what I did since I left CERN, with kind of going into financial services and then using that experience to actually combine it with my scientific experience to build a leading quantum tech company. And I think that is, of course, very thrilling if you have the opportunity to actually make use of all what you have learned so far in your life. With that having said, I think we are moving towards the Q&A section, and I'm very happy to answer some questions which you might have. Thank you.
Hello, Markus. So thank you for your presentation, for sharing your experience, telling us about your journey from particle physics to finance, and of course, like landing to the quantum computing world that we are all very passionate about in this, in particular in the last years. So I'm reviewing, I don't see any question right now from the audience. So if anybody has a question, I think you have a link to share your question. So please go ahead. So before I receive question from other people, I have let's start with the tough question, like the biggest question right now in the quantum world. So from your perspective, what is quantum computing next big challenge ahead?
Of course, the hardware development is decisive. We see that with the current leading kind of hardware typology, which is usually based on superconducting qubits, you have those mechanical challenges actually to scale them and to get the performance higher, so that you have to error correct. So to get really scalable a scalable qubit platform, I think is decisive to kind of enter into that exponential speed up of compute power. But I see very promising, hardware efforts which actually have a wide range. I mean, we have it from the superconducting level towards room temperature based on photonics, and I'm pretty sure we'll see some great innovation jumps here. And if some of these technologies actually work, we could be all surprised how quickly then those hardware will scale up. And that, of course, opens great doors for applications, optimization, and simulation challenges, which we can tackle, which we haven't kind of thought before, or which will be absolutely, which will mean absolute breakthroughs, I think, in the way we can optimize and simulate things.
We have a question from the audience, from Virko, I think. So what did you mean about hardware simulated qubits? If you can clarify this.
Yes. So our platform currently doesn't work with kind of real qubits, where you have a qubit which is cooled down to superconducting level and then kind of works. But our virtualized qubits are based on classical high performance computing architecture, but they are composed in an IP relevant manner, e.g. how we access the memory or so, to get kind of that simulation right, that you have kind of superposition and entanglement, so to say, at work. And you will not be able actually to simulate or virtualize, let's say, 100 qubits, right? The memory you would need is just too much, and it would be a contradiction to kind of an exponential curve, right? But in the current NISQ era, actually, you can do that. And e.g., 40 logical qubits, virtualized qubits on classical HPC, have a much, or at least our machine, much higher quantum volume, kind of a measure for what complex calculations actually can you carry out on that machine than the kind of real QPUs. We all hope that this advantage goes away very quickly and that we can switch on and integrate QPUs, which are much more performant, so which don't need that high error correction rate.
Yeah, and we are working on this. So
yes.
So one more question. So you mentioned object detection in autonomous driving. What is the main difference between these quantum algorithms and some classical algorithm for the same scope?
Yeah, the major difference actually is, the quantum algorithms are based on Schrödinger's wave equation, right? It's kind of real quantum physics at work, and that also means why that currently in that industry you really have to be a quantum physicist to work in that space and drive it forward. Yeah, that's actually a great chance for physicists, I would say. On the other end, that also means that you need quantum physicists, that you have to cope with the scarcity of global talent. So I can only encourage everybody to go into that field of particle physics, quantum physics, because the industry will need thousands and thousands of more quantum physicists working on that disruptive field in the future. And now, especially on the hybrid quantum neural network, which we built for autonomous driving, this is
Hello.
this is a
Hello. Hey.
This is an algorithm where
Hey.
where the neuron is encoded with a qubit, so it can have more values than just one value.
Okay, thank you. Sorry, there was a problem with the audio at some point. So can you share with us more about hybrid hardware and how this can increase the quantum volume?
Well, that actually goes a little deeper, so to say, in the technical layers of that virtualization layer, which I think would. I'm very happy to do that kind of offline, because you really would have to dig deep into our compute stack here, how that works, and it's actually also kind of patent based how we do that. But you can, I mean, there are other simulators out there where you can kind of do that, but it has a certain limit. And the differentiator with us is that we have a fully operational stack, which you can actually access via the cloud, and that we have APIs to all relevant systems. So what you can do with us, you can really have your quantum algorithm deployed, accessed via the cloud, and then deployed on our machine. And we are not depending solely on those the logical qubits. We can switch, we can act as an integration hub for real QPUs and switch between them. Yeah, but the operational stack is built in a way that it is more or less hardware agnostic. So currently we work with those logical qubits, but we could switch to real QPUs when they are better performant.
Okay, thank you. So one more question from me. So quantum computation science is a source of new technologies, and that we have governmental institutions that have joined the challenge and are supporting the field. And at the same time, there are industries that are emerging. There are several startups, and there are also well-established industries like big stakeholders that are in the field. So from your perspective, still, as someone that comes from CERN as government and now is in industry, what is the balance, or what is how do you picture different roles between these entities, government and industry and private sector?
Yeah, I think, and one would have to differentiate in the private sector. I think probably the big tech companies and the kind of the emerging ecosystem of quantum tech startups. For the latter, I mean, it really means kind of a little bit of mind shift. Yeah, as a scientist, you are very open and you prepare everything and you put it on archive and you publish it on Nature. If you are a commercial company who has institutional money backing it up, you of course have to protect your IP. So what you develop is usually yielding to a patent. So we file a lot of patents because these will kind of help us to defend those future markets. And I think that is a decisive difference, that we kind of are shifting from kind of a scientific publication mode towards the production of commercializable products. Yeah, but as much as we can, actually, as we want to actually really foster that industry, we actually put our developments on archive to actually help to boost that emerging industry.
Thank you. We have to wrap up. So one second question. What is your advice for young scientists and researchers that are listening to us?
I can say, I mean, if I would back at CERN, I couldn't say how my career would evolve. So it looks kind of so naturally, but it wasn't. I mean, looking back, I would say getting into physics, especially working at CERN, was one of the greatest decisions in my life. First of all, I'm so curious and I wanted to understand how life works and how the universe actually works. So physics is a great place to think about that. And with working at CERN, I think one is prepared for almost everything in kind of in an industrial career. The physicists, what we learn, I think, is you can use that in so multiple occasions. By the way, e.g. with BCG, I think the best performing group within BCG are actually physicists. Yeah, so I think it's a great preparation. I can only advise continue that path, and if I may allow, I think especially quantum physics has a great and bright future, because around quantum computing we'll see a lot of disruption in various verticals, and therefore more quantum physicists are needed, I think.
Okay, thank you, Markus. Thank you all for listening to us. I think we had like a great lesson, a lecture on how to merge physics and the financial world. So I think we are good here, and let's go to the next speaker. Thank you.
Thank you.